Welcome back, students. So in the last lecture, what we saw was how to model a real life problem into a graph and then use the concept of graph coloring to solve a specific problem related to the graph. Now, in that context, we introduced the term chromatic number, which basically represents the minimum number of colors which are needed to paint the vertices of the graph in such a way that no two adjacent vertices have the same color. This particular graph that we talked about, for example, used three colors: violet, then yellow and red. So the chromatic polynomial for this graph chi g was equal to 3. And we also talked about k colorability. So any color, any number of colors more than the chromatic polynomial can be used, and in that case, say we use 4 colors for this graph, we say that this graph is 4 colorable. Now we will start with the different theorems related to the chromatic number. The first theorem is related to complete graphs. As we all know, a complete graph is such a graph which have all the vertices adjacent. So this is a complete graph. This is a K4 we call it, which is a 4 vertex complete graph. Now, as you can see, since all the 4 vertices are adjacent, right? Therefore, if I start putting colors to the different vertices, so violet has been put on the first vertex, I cannot put violet in any other of the vertices. Now I put yellow in the second vertex, but the other 2 vertices are also adjacent to this vertex, so I cannot use yellow for the next time. I use red for the third vertex, but again the fourth vertex is adjacent to the third vertex. I cannot use red, and that's why I have to use the fourth color, which is green, for the fourth vertex. So that means my chromatic number, the chi of K4 of a 4 vertex complete graph, is equals 4. And if I generalize, the chromatic number of a n vertex complete graph is equal to n. This is the first theorem we have, and this is related to the complete graphs. Now I come to the next graph, which is a cycle. So what is a cycle? Where we have the vertices one after another and they form a closed loop. So this is like a cycle. I have 5 vertices in this cycle: 1, 2, 3, 4, 5. The way I can color these vertices is I can start with a red. So I paint this as red. I cannot paint this as red, I cannot paint this as red, but I can paint this vertex, the third vertex, as red. Okay? Now I use another color, the second color, yellow, for the second vertex, and I can also use yellow for the fourth vertex, right? Now the fifth vertex, I cannot use a yellow, I cannot use a red, because it is adjacent to the vertices which are either yellow or red in color. So I have to use a violet here, right? So what I do is I have to use 3 colors. So if I represent the cycle having odd number of vertices, so C2n plus 1 is general form, so the chi of 2n plus 1 equals 3, because the same thing will be extendable when the number of vertices increases to either 7 or 9 or any other odd number, where n is equal to odd, right? So any cycle having odd number of vertices have chromatic number equals 3. Now if I change this to an even number of vertices, say I add another vertex here, so now this cycle has 6 vertices, 1, 2, 3, 4, 5, 6. Now I can paint this 5th vertex definitely as a red because it is not adjacent to this vertex which is a red. And I can paint the 6th vertex as a yellow because the 2 adjacent vertices of this one are red in color. So we can see that using 2 colors I am able to color all the vertices of this graph. So that is extendable for any value of n, any even value of n, and we can write it as chi of C2n equals 2, or the chromatic number of a graph having, or of a cycle having even number of vertices is 2. So these are 2 basic theorems of the graph coloring related to standard graphs. Now for the graphs which are not standard, or what I mean to say is general graphs, it is not a complete graph, it's not a cycle, it's not a path, it's not a tree, so it's a general graph. How do I calculate the chromatic number? Again, there are very specific theorems to find out the, or related to the upper bound and the lower bound of the chromatic number for general graphs. Okay, so first I will explain the theorems related to the lower bound of chromatic number and the theorems related to that. Before I do that, quick background about 2 important concepts in graph. The first one is called a independent set and the second one is called a clique. So say for example I have a graph A, B, C and D. Okay, the vertices or the set of vertices of the graph which are not adjacent to each other is called an independent set. So in this particular case, B and D, they are not adjacent to each other. So this set BD is a independent set. And in a graph, the independent set which is largest in size or which has maximum number of vertices as a part of it is called the maximal independent set. And the cardinality of that independent set, so the cardinality of this particular independent set is 2. So the cardinality of the largest independent set of a graph is called independent number and is represented by alpha of G if G is the graph. So this is the independent number. Okay. Now what is the clique? Clique is just the opposite. So the vertices which are adjacent to each other form a clique. So in this particular graph, A, B, C, these 3 vertices are adjacent to each other. So this A, B, C represents a clique. Okay, and the cardinality of the clique, so in this case it is 3, is called the clique number and represented by small omega G, and this is called the clique number. So how does it relate to the theorem related to the theorem of chromatic number? The theorems say that when we have alpha G, the value of alpha G in a graph, the chromatic number chi of G is greater than or equal to the number of vertices divided by the alpha of G. So number of vertices by the independent number. So chromatic number is greater than or equal to that. So that's the first theorem related to a general graph. What's the next theorem? When we have a clique number, the omega G, so the chromatic number chi G is greater than or equal to the omega G. That's the second theorem. We can use this theorem, and we will see that when we solve problems, we will see that we can use these theorems to solve problems, that is to find out the chromatic number for general graphs. I will pause at this in this lecture. In the next lecture, I will be talking about the upper bounds of chromatic number, the theorems related to that. And what I will do is I will also explain how to solve a problem using the upper bound theorems and the lower bound theorems of chromatic number. Stay tuned. Thank you.